what we've done so far, we've kind of been building up to this. We've shown how we can approximate an area under a curve, which translates to a definite integral by using geometric shapes. And we've been using different types of shapes, mainly rectangles and trapezoids. And we've seen that we can be more accurate with trapezoids, but we can also get a simpler formula with rectangles, specifically the right rectangular approximation method. So we have a simpler process with that. And then we've said if we want to get a more and more accurate approximation, we do what with the number of rectangles or number of trapezoids or whatever we're using. We increase it, right? And so if we increase it to a really big number of rectangles, then we get a more accurate answer. And the more we have, the more accurate it's going to get. And as some of you have predicted, if we can let this number of rectangles do what? Approach infinity, then what we're going to get is an actual value. We're not going to get an approximation anymore, but we're going to get the exact value. And so that's going to be our goal. To do that, we first need to work with this generalization here and get an expression for the approximation for just an arbitrary number of rectangles, just using n rectangles. And then we're going to use that and see what happens to that value as n approaches infinity. All right, so I'm going to go back to an example we've done before, and we're going to use the RRAM formula to approximate the value of this integral using n rectangles. So we generalize this with just f of x. So now we want to do it with this particular example. So the first thing we're going to do is the first thing we always do. We need to figure out what this delta x is going to be here. So when we had 100 rectangles, we took 3 minus 1 divided by 100. Since we have n rectangles now, what are we going to do? Yeah, so delta x is going to be 3 minus 1 divided by n, which is 2 over n. All right, so no matter how many rectangles we have, we can just put that into this formula right here, and that'll tell us how wide each one of those rectangles is. All right, then what I'll do is I'll go ahead and set up the approximation just like I normally do. So I'm going to have the integral from 1 to 3 of x squared with respect to x is approximately equal to this RRAM, and I'm going to put that in there just for a clear line of reasoning here. RRAM n, so n is going to be arbitrary now. It can be any number we want. And that is going to be equal to, well, delta x is 2 over n times the sum from n equals 1, I'm sorry, I equals 1, I keep doing that, I equals 1 to n. Again, we're going to leave n as a variable. We want to let that be any number we want. And then it's going to be f of a plus I delta x. So first of all, f of x is what? Yeah, so I'm gonna just write that here. F of x is going to be x squared. So in this sum here, we're going to have a plus I delta x squared. What is a? 1. So it's going to be 1 plus 2i over n squared. Here's the trick. We talked about summation a little bit at the end of last week. What I want to do is I want to simplify this sum, the sigma notation, and actually get rid of the sigma notation using the properties of sums that I know. The first thing I need to do that, though, is to simplify this expression. So I'm going to expand this, and we've done something kind of like this before. So when I expand that expression, I'm going to go to the next line here. I get my delta x is still out front, 2 over n, times the sum from I equals 1 to n of, so we're going to have 1 squared, which is 1. We've got 2i over n times 1, which is 2i over n, but then we're going to have 2 of them, so it's going to be plus 4i over n. plus 2i over n squared, which would be 4i squared over n squared. All right, so now let's remember our properties of sigma. I'm going to make this kind of small here to make some more room. First of all, if I'm taking the sum of a sum, so I've got 4 different sums here, what I can do is I can break it up into, I'm sorry, did I say 4? I've got 3 different terms here. I can break it up into 3 separate sigmas. Okay? The other thing I can do, and I'm going to do all of this in one step, I can factor out anything that doesn't have to do with I. All right, so this I right here, that needs to stay in the sum. But the 4 over n, that's just a constant. Now, you may be saying, well, we said that n is a variable. N's a variable in the sense that we can put any number we want in for n in this expression, but as far as the sum is concerned, n is staying the same. So as far as the sum is concerned, n might be 7. Okay, and so that's going to be 4 over 7. Okay, so as far as the sum is concerned, the n is a constant. It's not changing. Okay, what we could do with this is plug a number in for n at the beginning, and that number is going to stay the same through the whole problem. Okay, so I'm going to break it up into 3 separate sums, and I'm going to factor out anything that doesn't have to do with the I while I do that. So here's what that's going to look like. I've got that 2 over n out front still. And I'm going to distribute the 2 over n to each one of these also. All right, so the first one I'm going to have 2 over n times the sum from 1 to n of 1. That's the first term. Plus, I'm going to factor out the 4 over n. That's going to join the 2 over n, so what do I get there? 8 over n squared times the sum from I equals 1 to n of I, plus, for the last one, I'm going to factor out the 4 over n squared. And I've got the 2 over n out there, so that's going to be 8 over n cubed times the sum from I equals 1 to n of I squared. Now the great thing about this is I have formulas that tell me what this is, and what this is, and what this is. We're going to need those formulas. So we have our 2 over n times the sum from I equals 1 to n of 1. What's that going to be? This sum right here. That's just going to be n, right? So it's going to be times n. Then our next term we have 8 over n squared times what we get for this one. What's that going to be? Okay. And then our last one we're going to have 8 over n cubed times
n plus 1 times 2n plus 1 all over 6.
Okay, n times n plus 1 times 2n plus 1 all over 6. Now, this looks kind of complicated, but it's actually really simple compared to everything we've had up to this point. Okay, first of all, we can simplify some things. In every one of these, we've got an n that's going to cancel in the numerator and the denominator. So the n here cancels at the n here. One of the n's down here will reduce with this n here. Okay, so that'll go away. One of the n's here will reduce with this n here, and those are going to go away. And I know I can reduce these because I know n's not going to be 0. It wouldn't even make sense to say there's going to be 0 rectangles. That'd just be silly. All right, we're looking for n to be a big number, so we don't need to worry about reducing zeros there. There's also some other reducing that can happen. We've got an 8 and a 2 that'll reduce and give us a 4 out there. We've got an 8 and a 6 that'll give us a 4 and a 3 here. And so we're going to get something that looks a little bit simpler. This, if we simplify it, we're going to get 2 plus 4n plus 4 over n plus, I'm going to go ahead and multiply this out. So we have 8n squared plus 12n plus 4 all over n squared.
3n squared.
Thank you. 3n squared. And what can I do now? We could get a common denominator here, and so multiply this by 3n over 3n, and multiply the 2 by 3n squared over 3n squared. And so what we end up with then is, let's just go term by term. We're going to have 6n squared here. We're going to have 12n squared here plus 8n squared here is how many n squareds? 6 plus 12 plus 8, 26 n squared. Okay, and then our n's, we're going to have, looks like 12n here plus 12n here is plus 24n. And then our constants, we only have one, just at 4, so we'll have our plus 4 there, all over 3n squared. Okay, now, that's as simple as we can make it. So let's go ahead and put a box around it. What is the value? We just did a lot of work here, a lot of calculation. What's the value of this expression right here? What is it? And when I say value, I don't mean like what's the numerical value, but what does that do for us? Why is this a nice expression to have? Plug in any number of rectangles you want, and that's going to tell you the value of the approximation. So, for example, I'm not going to make you do this, but if we put 4 in for n, then it's going to give us, what do we get, like 10.75?
Sure.
We did. It was a long time ago. It was Friday. But it gives us the approximation with 4 rectangles. If we put 100 in there, it's going to give us the approximation for 100 rectangles. If we put 1 billion in there, it's going to give us the approximation for 1 billion rectangles, right? So we can put any number we want in for n, and if we want to make it more accurate, we just make that n bigger, and all we have to do is plug it in this expression and we're done. We don't have to come all the way back up here and plug it in up here and then do all the calculations for it, and then do it again if we want to make it more accurate. Okay, we've done all of that work. The trick here is going to be to see what happens, what are we going to do with this expression? Let n approach infinity. So we want to see what happens when n goes to infinity. To do that, what are we going to have to use? Limits. So we're going to have to look at what's going to happen with some limits when n approaches infinity, or when some value is approaching infinity. So that's our next step here.